Hi guys, welcome to this video on waves, P6. First lesson, this is a bit of an introduction to waves. So what we're going to do is look at what actually a wave is. We're going to define the keywords in waves. We're going to calculate using the period equation and then compare longitudinal and transverse waves. And then to finish off, we're going to be using the wave equation. So what's a wave? Well, a wave is a disturbance in a medium. So a medium is something a wave can travel through, i.e. something made of particles. So if you like, here is the medium, these are particles, and this here is the disturbance. Now if you look, what we're doing is that disturbance is oscillating. We are moving the particles backwards and forwards across a point. Oscillating is like a nice scientific word for vibrating, if you like. And when you have a disturbance, an oscillation in a medium, you transfer energy. You can see the energy going through the medium here, all the way around it. So the most common example you normally see in physics is when the physics teacher gets to get Slinky out. It's the main reason why someone becomes a physics teacher. So you can own a Slinky without being judged. If you look in either case, so Slinky has been oscillated that way, and the energy goes this way. And in this one, it's been oscillated up and down, and the energy goes that way. So a wave is where you have an oscillation that transfers energy through a medium. Think of a medium, for example, like sound. Well, it usually goes through the air. Air is the medium. It could go through water. If you're underwater and you're talking to someone, you can hear them. It can go through solids as well. Light is a bit of a weird one. Technically, what we say at GCSE is that light can go through a vacuum, but it's a disturbance in an electric and a magnetic field. So just bear with on that. Just take it for what it is, and when we get to A level, we'll tell you the truth. So what we do is we talk about these oscillations. We talk about, imagine you're looking at just one particle and you're focusing on that oscillation. So if you look here, we've got a graph of the oscillation. What we're doing is we're measuring the displacement over time. Now, displacement means distance moved in a certain direction. So what we're looking at is the particle normally has a rest point, which is here, and it's moving to and from that rest point, just like in these past ones, that the Slinky's a rest, but it does move to and from that rest point. And if you look, we can measure the displacement, and here, that's a damn fine line. And yes, I did even use a ruler. Those points there, that's the maximum amount these particles are displaced in all this. If you take a freeze frame, they might not be at that position, but they are displacing across that sort of rest point called the equilibrium. And this here is the maximum displacement, and they give that a name. It's called the amplitude. So amplitude is maximum displacement. You've got to look over here. Displacement in this case is measured in centimeters. So for this wave, the amplitude would be 1 centimeter. Now this is the sort of graph you're going to see with some numbers on as well. So if we're talking about this, that there is the amplitude. Just be careful because they will try and confuse you. They may draw a graph like this, and they may say, I don't know, that's 0, that's 5, that's -5. And they may say, right, what's the amplitude? And it may say A is 5, B is 0, C is -5, and D is 10. In this case, the answer is A, and it could be C. The reason why it's negative, it just means that it's going backwards, if you like. So if you like, positive is when this particle is going forward, and then negative is when it's going backwards. You can see the Slinky going back to its normal position now. A few other things you can get from this graph. So some keywords we're going to use. This point here, right at the top, this is called a peak. And this point down here, that's called a trough. Now the peak is the highest point of the wave, and the trough is the lowest point. Think of a peak like a peak of a mountain, and trough, well, pixies are troughs. That's the shape of a trough. And where do you put a trough? On the ground. A lot of people will look at this graph and go, right, I'm going to measure the wavelength. The wavelength is just there to there. That's a complete wave. It's the distance from there to there. That is not true. That was a graph of displacement against time. This is a picture of a wave. Wavelength is a physical distance of a wave. You can't get that from the previous graph. It's the distance from one point on the wave to the next consecutive point, i.e. in this case, they've gone from peak to peak. It keeps moving. I can't stop it. Peak to peak. That's the wavelength. You could even say it's from trough to trough. Oh, lightning skills. So on this graph, if you have a displacement time graph, that there is not the wavelength. That is something called the period. Think a period like a period of time. Period is the time taken from one oscillation. So if we go back to this, if you were to time how long it took for the wave to start at this point here, to go up and down and back to the start, it's that time there, the time taken for one complete oscillation. Now if you time that and you say, right, I'm going to time 1 second and try and measure how many times it does one complete oscillation, it's going to be tricky. Best thing to do, time for something like 10 seconds and then divide your answer by 10. You'll be much more accurate because of human error to do with timing, reaction time. So that is the period. And period you measure in time, you measure in seconds, or whatever it says on the graph, because it might not say seconds. Another key word is frequency. Now frequency, if you think of something, how frequent something is, frequency is how often. And it's how often you have an oscillation, i.e. how many oscillations in 1 second. So again, same thing, what you want to do is you want to time how long it takes for one complete oscillation. Frequency is also defined as the number of whole wavelengths that pass a point in a second, because every time you have a wavelength moving a certain distance, or sorry, if you have this wavelength here, move from there to there, the time taken from there to there, for the wave to move from this point to this point, is actually the period. It's the time taken for one complete oscillation. So they define frequency as the number of complete oscillations per second, or the number of complete wavelengths to pass a point in 1 second. Frequency is measured in hertz, capital H, little z. So if you were to look at this wave, we can try and measure the frequency, i.e. the number of waves that pass a point in a second. I'll tell you what, if we measure that there, so we go 1, 2, 3, 4, 5, right, that took 5 seconds for one wavelength to pass a point. Frequency is how many wavelengths pass a point in 1 second. So if it took 5 seconds of one wavelength, it would be 0.2 waves passing a point in 1 second. Or another way they say this is 0.2 hertz. So look, here's a graph. Pause the video. What I need to do is tell me as many things as you can about this wave. So if we look, a few things, there to there or there to there, the amplitude is 0.2 millimeters. Look at your units. And then there to there, that's the period. Period is 4 seconds. Period, capital T, period is 4 seconds. Frequency, right, now that's where we go on to an equation, which is this one. Period is 1 over frequency. Now this equation you don't need to remember, you get given it. So if we go back here, I always find the best way to do an equation is to write out the equation and then write it out again with the letters missing. So it looks something like this. Something equals something over something. And then what you need to do is shove the numbers in. So we know the period is 4 seconds. I want to know what the frequency is. 1 over the frequency is 4. Now to rearrange this, some people can do it in their heads. To rearrange it, I times both sides by f. So you get 4f equals 1. Then it's a bit easier to arrange now. Divide both sides by 4, and you get f equals 1 over 4, which is 0.25. We're running out of room. 0.25 hertz. So you get a quarter of a wave every second. So after 4 seconds, you will have one wave. So just remember that equation you get given to you. Here's some practice. Again, pause it and then have a look through the answers when you're done. There you go. They're the answers. So if you want another practice of this one, pause it and we'll go through it in a second. Okay, answers. So that there, not a straight line. That there's 0.3, that's the amplitude, 0.3 millimeters. And then the period, again, look, Period is 4 seconds. We just did this one. The frequency is 1 divided by 4, 0.25 hertz. Remember the unit hertz. Right, so next point, longitudinal and transverse. So there are two different groups of waves to do with the oscillations. Both of these waves have oscillations. If you look, the particles are moving backwards and forwards. And in this top case here, the particles are moving that way and they're moving that way. The energy, this is what's putting in the energy over here. The energy is going this way. And with this wave underneath, again, the energy is going that way, but the oscillations are that way and that way. So this is what defines these two types of waves. The top one is a longitudinal wave. And the bottom one is a transverse wave. A longitudinal wave is where the oscillations are parallel to the energy. So look, these arrows here are parallel to that arrow there. The oscillations are parallel to the energy. If we look at the transverse wave, they're not parallel anymore. These here, if you were to compare that line with that line, they are perpendicular. So what we say for a longitudinal wave, the oscillations are parallel to the energy transfer, and transverse wave, they're perpendicular to the energy transfer. Good little way to remember this. You might think this is absolute rubbish, but hey, see if you use it, it might come in handy. I have a little trick of remembering each one. So it depends on how you write the words. Why don't that go? It depends on how, it's fine, I like it there. It depends how you write the words. So longitudinal, look. Longitudinal and transverse. Right, longitudinal. Do you notice about all these letters? They're all parallel to each other. Longitudinal, the oscillations are parallel to the energy transfer. Transverse, look, there's a cheeky little right angle in there. Perpendicular, the oscillations are perpendicular to the energy transfer. Could even say, look, that looks like a transverse wave there. Bit of a tip here. When you have these graphs, so we go for that one, for example, you might think, oh, what type of wave is that? That there is a transverse wave. Wrong. It could be either. This is a graph of displacement against time. So what you're doing is you're focusing on a particle. So if we go back to this one and we say, right, look at that particle there. What I'm going to do is I'm going to measure its displacement over time. That's exactly what this is a graph of. It could be, look, I'm going to pick that particle there. I'm going to measure displacement over time. It doesn't matter which way it's going. It just means it's going backwards and forwards across its like rest point, its equilibrium. So when you look at this, don't think it's a transverse wave. It could be either. If it was just a picture of a wave like that, then yes, it is a transverse wave. But if it's a displacement time graph, it could be either. Good thing to note on here as well is that the medium's not actually going anywhere. I mean, it's moving backwards and forwards, but it's not going anywhere. That red dot, keep your eye on it. All it's doing is it's oscillating backwards and forwards. So when you talk, the air in front of your mouth is not going to the other person's ear. It's just transferring the energy via oscillations. If you look at this is a water wave. So it's a transverse wave because these are going perpendicular to the energy. What you can say is if you look at that particle there, that particle's not actually going anywhere. It's oscillating, but it's not really going anywhere. A good way of proving this, which is what they like in the exam, is a cork. So that there, oh my god, this could be a good drawing. Well, it's a mushroom. If you put a cork on water, it will bob up and down. Now that's showing you that there's energy going through the water, but if the water was moving, the cork would be moving that way. It isn't. With longitudinal waves, there are 2 points to note. So you have these areas here and these areas here where you have high pressure. They call that areas of compression, where the particles are squashed together. You have these areas here, areas of rarefaction, low pressure, where the particles are spread out. And you can measure the wavelength by measuring the distance from compression to compression. You could do rarefaction to rarefaction as well, but usually compression to compression. I know it's stupid. I mean, why would you use that word rarefaction? It's very similar to another word in physics. I just think rarefaction, rare, there's not many particles around here. Quite rare to find. Okay, final thing is using the wave equation. So this equation is one of the 23 that you've got to remember. I know. So it comes in symbols, it comes in words. If you just like the words, then here it is. If you like the symbols, V is the symbol for wave speed. Don't ask why, just accept it. F is frequency, that's nice. And then, whoa, what is this? That's the symbol for wavelength. It's called lambda. It's like an upside down, backwards Y. It's just a symbol for they use. Frequency, as you said earlier, measured in hertz. Wavelength in meters. Wave speed in meters per second. Just check. You might need to convert something. For example, usually what they like to do is put something like that, kilohertz, which means 1,000 hertz. I always say with equations, change it straight away because then it's just done. Wavelength, meters, again, could be that. It could be in standard form as well, just watch out. So here's a really basic one. Wave's got a frequency of 100 hertz and a wavelength of 2 meters. What's the speed of the wave? All you do is you just substitute in the numbers. Remember I said, write the equation without the words or the units, the symbols in. 100 hertz, that goes there. Wavelength 2 meters, that goes there. What's it? Well, 100 times 2, 200 meters per second. Yay! Right, have a go. Here's some practice. Pause it, we'll go through it. Right, just wanted to go through one of them, which is this regular one, just to show you about rearranging. So V equals F times lambda. We know what the speed is, 330. And what I said, substituting the numbers you've got, we can work out the rest later. Wavelength's 3. We don't know this, so let's just call it F. Now, basic rearranging here, we want F on its own. We divide both sides of the equation by 3. What we get is 330 divided by 3 equals F. 330 divided by 3, 110 hertz. Now, what they like to do is they'll like to bring in the period equation as well, as we've got in here, and they will also bring in standard form. This number here, that is the speed of light in a vacuum. Just be careful, just make sure you're aware of how to do standard form. Good, well, hope you enjoyed that, guys. See you later.